last class, and we were satisfied with that discussion. Okay, we found that the partition function was nice and modular invariant. Now, free bosons are not the only free theories in 2 dimensions. Free fermions as free bosons. And in every dimension, both free bosons and free fermions give examples of conformal field theories. Okay. This is, by the way, not true for instance, free U1 gauge fields. Free U1 gauge fields give examples of conformal field theories in 4 dimensions, but not in other dimensions. Okay. And there's an interesting reason for that. But free bosons and free fermions are conformal in every dimension. Okay. So today we're going to start studying free fermions, and if we go well, we will start seeing the equivalence between bosons and fermions in 2 dimensions. Okay. So the action that we are interested in is the free Dirac action. I think I will put a 1 over 2 pi here, but I may have to change that as we go along. Psi bar del slash psi. So we want to study the free theory of massless fermions. Because it's massless, this is the action. Okay. Now, this would be the action for fermions in any dimension, but we're in 2 dimensions, so things are easier than the general dimension. So we can make explicit how easy this thing is. You know, the painful thing about studying fermions in higher dimensions is these Dirac matrices, right? The spinor indices and so on. 2 dimensions, everything's so simple, the indices sort of drop out. So let's see how that works. We want to choose a convenient basis for our gamma matrices. Gamma 0, we will choose to be I sigma 2. So why I sigma 2? You see, we have 3 sigma matrices in 2 dimensions, 2 cross 2 matrices, sigma 1, sigma 2, and sigma 3. Now, sigma 1 and sigma 3 are real matrices. Sigma 1, sigma 2, sigma 3 are all Hermitian. Okay? But sigma 1 and sigma 3 are real matrices, whereas sigma 2 is a purely imaginary matrix. Now, you remember that when we are studying Dirac equation in Lorentzian space, we need gamma 1 to be gamma 1 diagonal, but gamma 0 to be minus gamma 0 diagonal. Okay? So, we have to put an I in front of one of sigma 1, sigma 2, and sigma 3 in order to get gamma 0. And it's convenient to put the I in front of the matrix that was purely imaginary, so that all our gamma matrices become purely real. Okay? That's convenient from many points of view, one of which will be to see that you can make, as we will see, you can make real spinors, real chiral spinors in 2 dimensions. Okay, so for this reason I've chosen gamma 0 to be I sigma 2. Okay, now the other ones of course are up to you, but it's convenient to choose gamma 1 to be sigma 1, I would imagine, and gamma 5, you know, the chirality gamma, to be sigma 3. Okay, so let's make that choice and then see what the Lagrangian becomes. Okay, so I'm not carrying this 1 by 2 pi along, or partly because I may have to change it. So so this is psi star. So psi bar is psi star with a gamma 0. Gamma 0, which was I sigma 2. And then we have, gamma 5. Psi bar, psi star with a gamma 5. It's a sigma 3. Then we have gamma 0, so I sigma 2, then del 0. Okay, plus sigma 1 times del 1. Why gamma 5? Sorry, gamma, thank you, gamma 0. Thank you, gamma 0. Gamma 0. So I sigma 2. Okay, good. Okay, so we have Lorentzian. Minus, well, these are gamma upper. Yeah, gamma mu. Yeah. Okay. Yeah. So okay. So thank you. So let us see what this gives us. So this is I times I and sigma 2 squared. Sigma 2 squared is identity, and I times I is minus 1, so minus identity times del 0. Okay, and this one is sigma 2 times sigma 1, which is minus I sigma 3. And that there's an I, so we get plus sigma 3 times del 1 times I. Okay, and so we have let's so this matrix here, so this psi star, and I'll write this 2 cross 2 matrix out. So that's minus del 0 plus del 1, 0, 0, minus del 0, minus del 1. Okay? So let's write out this psi star. Let's write it out as, you know, a 2 cross 2 column. So let's write psi is equal to psi 1, psi 2, and psi star is equal to psi 1 star, psi 2 star. Okay. Since this matrix is diagonal, we see that we get psi 1 star minus minus del 0 plus del 1, psi 1, plus psi 2 star minus del 0 plus del minus del 1, 1, psi 2. Okay. Okay, and now let's look at okay, fine. Perfect. So this is del 1 minus del 0. And this is minus, yeah, minus of del, right. Okay. So up to some overall sign that we can pull out, this is so this is minus of psi 1 star del 0 minus del 1 psi 1 plus psi 2 star del 0 plus del 1 psi 2. Okay, you minus overall outside. Yeah, and you identify this as the left moving derivative, and this is the right moving derivative. Okay, so you see that psi 1 and psi 2 first decouple from each other. Okay, the second thing that you see is that the Lagrangian for, let's say, psi 1, which I'm going to call psi from now on, is psi del plus psi, if we call this del plus. Okay, and one of them will go into Euclidean space into psi del bar psi. One of them will be psi del bar psi, psi star del bar psi, and the other one will be psi star del psi. Okay, so you see the first thing that's important here is that this Lagrangian here decouples into two Lagrangians, one of which has an equation of motion which is del bar psi is equal to 0. That's this guy. The equation of motion for this guy is del bar psi is equal to 0. The other one which has an equation of motion that's del psi is equal to 0. The guy which has del bar psi is equal to 0 describes a purely holomorphic field because its equation of motion is del bar psi is equal to 0. The guy which has del psi is equal to 0 describes a purely anti-holomorphic field. So we see that this fermion here decouples into two fermions, one of which is purely holomorphic, the other one other of which is purely anti-holomorphic. Okay. Now the next thing we see here is that we've got this field and its complex conjugate. Okay, but exactly in 2 dimensions, I mean precisely for the reason that this Lagrangian was purely real. Okay, it is possible in 2 dimensions, as you know very well. To impose the condition, the reality condition, psi is equal to psi, psi star, if we want to. The equation of motion allows it. Everything is consistent with it. Okay, so that was the fact that the reality condition became so simple was the point of choosing this Descartes matrix. Okay, we will sometimes deal with complex fermions, sometimes with real fermions, according to the whatever is convenient for us. Okay. Now Polchinski's notation is a bit confusing. He writes this action as psi bar del psi. Okay, and so I'm going to follow his notation, but we want to remember that psi bar has nothing to do with anti-holomorphic. Psi bar is just the complex conjugate of psi. Okay, psi bar and psi are both holomorphic fields. In one way of thinking of this is, psi and psi bar, you can take linear combinations of psi and psi bar, psi plus psi bar by square root 2, and psi minus psi bar by square root 2 divided by an I. These become two real holomorphic fields. Is this clear? So when I talk about psi bar, that this has nothing anti-holomorphic about it. Now question, how can it be that I've got a holomorphic field, but its complex conjugate remains holomorphic? Wouldn't you think that if I take a holomorphic field, its complex conjugate become anti-holomorphic? Question? Exactly. So this is the same thing that we've discussed many times. Complex conjugation always happens in Lorentzian space. In Lorentzian space, this was a Lagrangian. And del plus this is del 0 minus del 1 is a purely real operator. So complex conjugate leaves it invariant. So psi and psi bar, psi star obey the same equation of motion in Lorentzian space. When we say complex conjugate in Euclidean space, what we are doing is carrying the notion of complex conjugation from Lorentzian space to Euclidean space. Okay? In Lorentzian space, psi and psi bar obey the same, psi and psi star obey the same equation of motion. So the same must be true in Lorentzian space, in Euclidean space. Is this clear? So psi and psi bar, despite being complex conjugates, are both holomorphic. And this is consistent because the notion of complex conjugation is, for physics, is only relevant in Lorentzian space. And then Euclidean space, which is a tool, inherits that notion. Okay? Excellent. So this is the theory we're going to study. Sometimes we'll take psi bar equals psi, because that's when we impose the reality condition. Sometimes we'll allow them to be independent fields, psi and psi bar, complex conjugates of each other. This is the theory we're going to study in the rest of this lecture. Okay? Great.
Can we define these gamma matrices?
Yes.
So gamma mu, anticommutator must be equal to metric. And since we started with Lorentzian, it is minus 1.
Yes. Had we done sigma 2, we would have got delta. I sigma 2 gives us the Lorentzian metric. Okay? By the way, I never said it, but it's clear to you that the chirality matrix here was sigma 3. So the guy that's holomorphic, which was 1, had eigenvalue 1 under the chirality matrix. Okay? Whereas the guy that's anti-holomorphic, which was psi 2, had eigenvalue minus 1 under the chirality matrix. So the holomorphic and anti-holomorphic go with chiral and anti-chiral. Is this clear? Okay, great. Fine. So now that we know what theory we want to study, I think we want a 1 over 2 pi, but I may have to modify that as we move along. Let's study it. Yeah.
Suppose we start something with some curve pattern.
In a curve pattern, yes.
Okay. Then we have to add this
Spin correction.
correction.
Yes.
Now, from what I understand, you can always take this
Yeah.
metric to perform the UV equivalent to the flat.
Yes.
How does that work?
How does that work? Yes. Okay. So as you have as you mentioned, every metric in 2 dimensions is while equivalent to just flat space. This is equivalent to the following statement, okay, that in every metric, up to that overall Weil factor, we can always choose patchwise to make the metric just flat, up to Weil factor. Because this theory is going to turn out to be conformally invariant, as we will see. It's Weil invariant, so the Weil factor does nothing apart from that overall factor in the partition function. So, in every manifold we will have patch of completely flat. So this analysis that we're doing is valid in every patch.
Right.
Okay. What we will have to be careful about is about the signs we get when we go across go match across patches.
Yes.
Okay, the spin structure.
Yes, the spin.
Okay, so that we will be careful about. Okay, for instance, we will already need to be careful about it when we study the theory on a cylinder, because a cylinder is not flat space.
Yes.
You need two patches for the cylinder. Okay, and that will force us to introduce both the Nebu-Schwarz and the Ramond set. Okay, so that's the kind of thing that, okay, we get all kinds of spin structures and genus G Riemann surfaces. Was that your question? Yeah. Yeah. Okay, excellent. Okay.
But
So
the metric we choose on the cylinder is flat minus dt square plus pi square.
yes, the metric we choose on the cylinder is flat, but the cylinder has an identification, whereas R2 has no identification. So if we want to think of cylinder as being patchwise R2, then we need two patches, or maybe even three, depending on how you think of it. A mathematician might even say three. Anyway, yeah. But you know what I mean, right? That we need one patch here on this part of the cylinder, another patch on that part of the cylinder, and then specify how we transit between the two patches. The key thing with fermions is that physical things with fermions are always bilinears in fermions. So you're allowed to put minus signs in the transition rules. Psi on one patch could be minus psi of the other patch. Okay? And that allows for, so suppose I take the cylinder, think of this patch and that patch. So I call it the northern patch and the southern patch. Now each of the northern patch and southern patch overlap in two places, two disconnected regions. Now if you make the transition rule that the sign is +1 here and +1 here, okay, then you get that this is like being on the cylinder with periodic boundary conditions. If you make +1 here and -1 here, you get anti-periodic boundary. If you make -1 and -1, you're just dealing with the wrong fermion. You redefine one of your fermions to minus psi, and then it's back to +1 and +1, and you're working with periodic boundary. Okay, so it's just that. This complication in the end amounts to just the choice of the spin structure.
So the structures, the coordinate matches correspond to the sectors of.
The patching between coordinate matches correspond to the sectors. Okay. Okay. Excellent. A psi bar psi will always be positive. I mean, in any patch it's positive. Yeah. What? It will be the same on both sides, because that's the reason we are allowed to do minus signs, because the Lagrangian, for instance, or stress tensor, whatever, it's always bilinear in fermions. Anything physical is bilinear for us. Okay? Excellent. Okay, so let's continue. Let's first look at this action. E to the power, we're interested in d psi bar, e to the power minus 1 by 2 pi psi bar del psi. Yeah.
In this context is using Grassmann variable, right? So what kind of statistics?
What kind of statistics? Statistics, just the usual. In operator formalism, the oscillators will obey anti-commutation relations. It's the usual thing. So this, as you said, this path integral is defined as a path integral over Grassmann variables. Okay? And the Hilbert space interpretation of that is the usual, that each oscillator is an oscillator in a two-state system. By the way, I'm not planning to review that here, but if those of you who have not seen, I remember when I was a student, I was reading Bjorken and Drell because that was the book available when I was a student. Okay, and they've said, okay, they had this very nice canonical quantization and so on for bosons, and then they say for fermions we just changed to anti. Why? Where did where did that come from? Okay, and the time I really understood it, I felt I really understood it, is as follows. You see, I feel that a good way to try to understand one way you can formulate the theories in terms of a path integral, and then to obtain the Hilbert space, you cut the path integral, and then you get what you get. Okay. Now it's this beautiful fact that cutting a path integral like this, or even a quantum mechanical path integral like this, produces a Hilbert space. Let's do a quantum mechanical version of this. So just A dt B, where A and B are both anti-commuting variables. This produces, if you cut it, you see a two-state system. Okay? If you've not worked this out for yourself, I strongly urge you to do it. And if you find it difficult, look at the relevant appendix in Pulchinski, who's worked it out, beautifully. By beautifully, I mean not very elegantly, but very explicitly. Okay? So
My question is mostly regarding two-dimensional.
yes.
We don't have like spin. So
What do I mean by fermions in this case? Excellent. So there are two things about fermions. Like, one is just that its oscillators are oscillators that obey anti-commutation relations. That's all I mean. I don't mean anything about spin statistics or yeah. Yeah. For the excellent reason that there's no spin in two dimensions. Okay. This is a quote from Coleman. Coleman has, I think, either his paper or his book. Spin statistics doesn't work in two dimensions for the excellent reason that there's no spin. Okay, excellent. So let's continue. Okay, so we have this Lagrangian, and we want to figure out things about the Lagrangian. Okay, so the first thing I want to do is to figure out the Green's function. We're going to imitate an analysis of the bosons. So this time we're just going to do it, we're just going to use the path integrals all the way through. Okay, so let's see, and you're going to have to help me keep my wits about me with the signs. Okay, so let us first look at del by del psi of psi of z e to the power I by minus 1 by 2 pi integral psi bar del psi. This, as always, is 0. In fact, it's 0 for fermionic path integrals without even talking about what happens at infinity. It's just 0 because this guy and this guy just kill each other. Okay, so this is equal to 0. So 0 is equal to this. And now we open it out. Okay, so let's say that this is at z prime. Okay, so the first term is delta of z minus z prime, or delta 2, let's call this x and x prime. Delta 2 x minus x prime. By definition. 2 dimensions. Right? Now the next term, when I take this derivative through the psi, I pick up a minus sign. Okay? And then I differentiate. The way I've written it, when I take the derivative through psi bar, I pick up a minus sign. So the minus sign has gone away. I've got an extra minus sign here, which I'll have to check with. Let me check this. Sorry, just. It's here somewhere. S is equal to 1 by 2 pi. Good, so I've got a minus. I think that's right. Okay, so I get an overall minus sign, minus 1 by 2 pi. When I take this through here, I kill that. But then I integrate by parts. And I wanted del bar. So I integrate by parts. So overall, I have no minus sign. So one minus sign, another minus sign, and minus sign and integration by parts. So overall, nothing. So plus del bar of psi of x, psi, and let's call this, this was x prime, right? Because psi of x prime. And this is del bar prime. This is equal to 0. Is this okay? Yes.
So I know Grassmannians are AB equal to minus B.
Yes.
Now this del by del psi x at x prime is like an operator.
Yes.
So I will call it D.
Yes.
D of A is equal to minus AD.
Yes.
So I didn't get this, why this is true.
Yes.
And the other is, what's the action of keeping this del by del psi of psi bar?
What is the action of, say again?
What's the how does this operator act on psi bar?
Which operator? This one?
Yeah.
Psi bar is independent of psi. So psi and psi bar are completely independent variables. Okay, you can just think of them as completely independent Grassmannian variables. Okay, now why the derivative when it goes through, produces a minus sign? This is a definition of, you need a Leibniz rule. So suppose I give you del by del A. I've told you the rule, right? Is del by del A on A is equal to 1, del by del A on 1 is equal to 0. That's the usual rule for Grassmann variables. Now, I've got two Grassmann variables. I need to tell you what is del by del BA. Okay? Well, one way to work it out is this. The rule you could take as being always change the quantities so that A is the first guy, then use the rule. Okay? So when A is right at the beginning, the derivative hits it and gives you 1. Okay? Now, if that is the case, let's work out what del by del BA must be. This is equal to minus AB. Okay? So it's so let me write it properly. So del by del A of BA is equal to minus del by del A of AB, which is equal to minus B. But you summarize this rule by saying every time you take A through a Grassmann variable, you pick up a minus A instead of doing this complicated operation each time. Okay? Okay, excellent. Fine. Was that all questions? Okay, excellent. There should be a psi bar. Thank you. Yes, del bar psi bar. Yeah, it's always confusing when you say del bar psi bar. Remember, psi bar is also an anti-analytic function. Yeah. Okay. Excellent. So this is our equation of motion. Okay.
So I will set it out. So
Please.
Del bar will act on psi and psi bar or just psi bar? Bar will.
This bar is prime. It acts only on the prime coordinate. See, where did it come from? It came from here. This had a dummy, was an integral over y, let's say. Yes, the variable, the two-dimensional space, let's say was parameterized by y here. Okay? Now, this y here is set equal to x prime because of this derivative.
This is a
Delta function. Okay? So x prime has become y.
No, but my question was psi and psi bar, they are holomorphic or like?
Just think of them as completely independent variables. You see, one way of thinking of this is psi is equal to psi 1 plus I psi 2 by 2, square root 2. And psi bar is equal to psi 1 minus I psi 2 by square root 2. Okay? Now, when I write del by del psi bar, think what I'm doing is doing the appropriate chain rule differentiations on psi 1 and psi 2. Do you understand what I mean? You can differentiate with respect to psi 1 and psi 2 independently. They're just independent real fields. And then you can differentiate with arbitrary linear combinations. I'm going to choose the linear combinations that would make this del by del psi by the chain rule. Okay? Equivalently, because psi 1 and psi 2 are completely independent fields, psi and psi bar are completely independent. It's like in complex analysis. When we say del by del z at fixed z bar, it's like that, right? Okay? There's nothing. Is this clear? Okay? Yeah, but if ever you get confused, move to the real variables. And what I mean by del psi is always the linear combination of those del by del psi that you would get from chain rule. Okay? Excellent. So let's keep going. So we've got this rule. We've got the rule that 1 by 2 pi del bar of psi x psi bar x prime del bar prime is equal to delta function. What? Minus. Okay. And now, am I getting a factor of I off? Okay, but anyway, let's move and see. Okay, so now I want to know what this must be. But clearly, this then is going to be proportional to 1 over z. Okay, as you know, del bar of 1 over z is a delta function. Okay, now we have to figure out delta function with what? Is a delta function with some number. Okay, with what number? One way to work this out. One way to work this out is to remember how it worked with the log. Okay, so we know that okay, we know del square of, I'll just do it carefully just to make sure we get it right. Okay, so del square of log r is equal to 1 by r sorry, del squared log r, suppose I take del squared log r and I integrate, this is equal to del of log r, which was equal to del dot r hat by r, which was equal to 2 pi. Okay, so this guy is equal to 2 pi delta of r, right? So, but this del squared, now you'll have to help me with what was my conventions with del. I'm so sorry about all this irritating stuff. Oh, I'm tempted to. Anyway, let's work it out. Del square, I'll just look at the conventions. So, yeah, del z was del 1 minus I del 2. Del z is equal to del 1 minus I del 2. Del z bar was equal to del 1 plus I del 2. And del z had the half, no, with the half. Okay, and therefore del z bar is equal to 1 by 4 del square. Okay, So we have, this is, okay. So we had this, so we had del squared of log z bar was equal to pi delta of r, 4 pi, because this is z bar r squared. I'm sorry about this. It'll be done in 2 minutes. Okay. It's 4 pi delta of r, and therefore, but del square was equal to 4 del z bar. So del z bar log of z bar, okay, was equal to pi delta of r. Okay, now let's take the del z, let's do it del z bar del z. Let's take the del z first, so that gives us del z bar 1 by z is equal to pi delta of r. Okay, and therefore we hopefully now can declare victory. So let's see, what did we have? We had our relationship was this, and therefore we see that I'm claiming, and you tell me if it's right, psi of z, psi bar of z bar, the psi of z prime is equal to 1 over okay, if I've done it right, it should be 2, but I know the right. Z minus Z bar. This is what I'm getting. Do you agree? Okay. Polchinski has 1 over Z minus Z bar, so we've messed up with a factor of 2 somewhere. Give me a minute, otherwise I'll leave it for you guys to fix the factor of 2. Let's see if I can fix it in a minute. Just a minute. Polchinski claims del z bar of 1 by z is 2 pi delta. So we messed this up. This is correct. Therefore, del square.
You should not, I think you should write this as del z bar del z plus del z bar. So one of them will not have log z.
I mean, yeah. Yeah, just perhaps, but give me a minute. I mean, I feel I could write it any way I want. Okay, just a minute. I've messed up somewhere. Just give me 1 minute. This was 2 pi delta. I think this is correct. Now this, therefore, if I do r square, it is 4 pi. That I think is correct. And was del z?
So what is the coordinate inside?
What? Maybe that's what you mean. Maybe his delta has a different meaning from our delta. But we derived our equation of motion using our delta.
There's a factor of 2 in the normalization of delta in the CC.
Yeah, it's okay. Forgive me, I'm going to make this a 1 for no reason I understand at the moment, and I will carefully go through the algebra and show you why it was 1 next time. Forgive me for that. Okay, there's some mess up somewhere. Okay. 1 minute more, it's just in here.
We have to replace r by z bar.
R squared is z bar.
On the delta side, other side. On the delta side. What is that variable r?
This was normal 2-dimensional delta function. Yeah, because I started with that.
You have to put half, then it becomes delta of r square. That will be replaced by z bar.
I'm not understanding. I mean, I'm using delta function as the normal two-dimensional delta function, so that integral of that is 1. Maybe maybe Pulchin's, now I know. Maybe his I know. Pulchinski writes his action, you guys were right. I'm writing d2x. Pulchinski writes d2z. And his d2z is extremely confusingly twice that. So the lesson was, I'll just get that. Okay, now we've tracked it down. The lesson is we started with the wrong action. Yeah, so just he writes it somewhere. Yeah, d2z is d sigma 1, d sigma 2. So he writes 2 pi with that 2. So we should have started with the pi. Okay. So now let's go. Sorry. So now we don't need to postpone to next time, hopefully. Our equation of motion came with a pi. Okay, pi. And now we're getting the right answer, right? Okay, so just correct the pi's through. Okay, so this is the right answer. Okay, so that was worth going through because we now know what action we're dealing with. Of course, there's no physics in the action, right? Because I can rescale psi and psi bar to whatever I want. But with this choice of action, psi and psi bar obey that combination, this direction. Okay, all good. Yeah, fine. Now let's move on. So we've got this nice 2-point function. We've got this nice 2-point function where psi of z, psi bar of z prime is equal to 1 over z minus z prime. Okay? Note, of course, that there's a non-holomorphicity because there's a pole here. And there's a non-holomorphicity in this guy, precisely at the location of the other guy. Okay? As in the case of bosonic theories, we're going to define composite operators in this theory by normal ordering. The normal ordering is again by Wick's theorem because once again it's a free theory. And once again we're subtracting away expectation value of the 2-point function. Okay? Now, this is the operator side of the free fermion theory. Okay? Let's go for a minute to the Hamiltonian side of the free fermion theory. Let's take the theory on the cylinder and study it. Okay. So now what we're doing, so what's going on? What we're trying to do is to study the theory defined by this Lagrangian on a cylinder where sigma belongs to 0 to 2 pi and time is time. Okay? If we did that exercise, the first thing we're going to have to decide is what periodicity we're going to give to our fermions. As we discussed earlier in this class, there are 2 natural periodicities to give. One is that fermions come back to themselves with plus sign. The other is that fermions come back to themselves with a minus sign. Okay? As you will see, in order to make sense of this theory as a conformal field theory, in order to understand how it gives a modular invariant partition function, for instance, we will need to include both sectors. But it turns out that the simpler of the 2 sectors, okay, the simpler of the 2 sectors is the one where you have a minus sign as you go around. Okay? So let's first study this theory in Hamiltonian language, where the fermions are anti-periodic as you go around the time circle. Okay? By the way, this is very familiar from thermal field theory. Thermal field theory, if you have fermions and you put them in Euclidean space, this Euclidean space is a thermal circle, fermions are required to be anti-periodic as you go around. just because trace of fermionic objects, when translated to path integrals, has antiperiodicity. Okay? This is a very familiar thing to do. I'm just going to start by studying this case because, as you will soon see, it's the easier case.
Here the antiperiodicity in the it's not in temporal
It's not time.
space.
This is a choice. Okay? We're not computing a trace, so we had a choice.
Why would there be a second case when it comes back to its own?
Why would there be a second case? Let's hang on and see why we'll need it. Maybe by the end of this class we will see. Okay. Yeah, I can immediately tell you a little bit. Okay, if you want, but maybe it's better to just wait. Just wait. Okay. It's sort of clear that modular. Let me just tell you. Okay. Consider a torus. Okay, and consider that you have determined that your fermion has antiperiodic boundary conditions on this cycle of the torus.
On sigma.
On sigma. Okay. Now we want to compute the partition function of this fermion. Okay. As we just discussed, when we compute trace e to the power minus beta h, we need antiperiodic boundary conditions on this cycle. So we put a minus here and a minus here. Okay, good, so we are happy. Except that there is a problem. There is a problem because, you see, if fermions are antiperiodic as you go around this cycle of the torus, and antiperiodic as you go around this cycle of the torus, then you can choose another cycle, which is this guy. Because it's antiperiodic here and here, it follows that it's periodic as it goes around that cycle of the torus. Okay, now if you want a partition function that treats the torus as a geometrical object, this identification for the torus is the same as this identification. So this boundary condition is not going to give you a torus partition function treated as a geometrical object. It's not going to be modular invariant. Okay? So you see, you're going to have to mix with some pluses. And once you get pluses in the game, you can treat that as the space. Okay? So minus and pluses, modular invariance forces you to consider both boundary conditions of the torus. So you'll never get a modular invariant partition function by looking at just minus. This is one way of saying the reason. We will understand in many ways.
But when you go sigma to sigma plus n, let's say,
Yes.
it will always be minus.
No. We are going to say that the Hilbert space has two sectors. Do you remember when we looked at winding strings? Okay? What was the assertion? The Hilbert space had an infinite number of sectors, one associated with each winding number. Okay? In one sector, we had one quantization. Another sector, we have another quantization. It will be similar here. The Hilbert space has two sectors. One sector is, in one sector the fermions are antiperiodic. In the second sector the fermions are periodic. And the full Hilbert space consists of the sum of both of these sectors, just like it consists of the sum of the winding sectors. That's how it's going to be.
Okay, so you're saying basically because of this two identifications, that sigma goes to sigma plus 1 and tau goes to minus 1 by tau, so that's why we should have like both identifications.
Yeah, if you want to make sense of the torus partition function as a geometrical object, which means depending only on the moduli of the torus, this will be needed. Now you can go back and question why you want to make sense of that. That's another discussion we can have. Why you're not happy. If you demand modular invariance, you need this. Okay, good. Right, so nothing will go wrong by looking at just the, okay, this by the way has a name, it's called the NS sector, Neveu-Schwarz sector. Okay, nothing will go wrong by looking at just the NS sector if you study the theory on the plane. Okay, but once you look at the theory on the torus, if you want various good properties, it will fail, as we will see as we go on. Okay, great. Other questions or comments?
Scaling dimension of size u.
No, scaling dimension of size half, as you see from this 2-point function. Right? Scaling dimension of an operator is half. Okay, but we will understand this we keep understanding this better. We will soon. Heisler. We could have looked at the stress tensor, but let me first do this. Okay. Okay. So we've got this theory. So what we're going to do is to take psi and expand it as follows. So we've got psi on the cylinder, which is a function of sigma and tau. Because psi is only has to be anti-periodic, we will expand it as e to the power I n plus half sigma, okay, times, let's call it psi n plus half. Okay, this will be the expansion in space. And then the time dependence will be fixed by the equation of motion. Okay, we know that the equation of motion fixes it to be, the equation of motion fixes this time dependence to be holomorphic. Okay, so we will get sigma plus t or sigma minus t depending on which sector we want. Yeah, let's say it's the sector where it's sigma plus t. So this is going to be our expansion of our psi operator. Okay?
The total will be this plus the sigma minus tau.
If we're looking at psi 1, it's just this. Psi 2 is the guy which is sigma minus tau. Right? So now we're just looking at psi 1, forgetting about that guy. So it's better than the boson, where that same X field had both left and right movers. Here we're looking at the field which has only left movers, let's say. Clear? Okay. Now, the next thing we have to do is to expand, to do the canonical quantization of this, and we will find the usual canonical quantization relations, right? Please.
The equation of motion were del bar phi equal to 0.
Yes.
And this Fermionic case it's del phi equal to 0, del bar phi.
Del bar psi 1 is equal to 0,
Yeah.
del psi 2 is equal to 0. It's exactly like that, right? So it's like square root of that thing, as fermions often are, right?
Well, there is a n plus half.
The half is because we want it anti-periodic,
Oh, minus of. Okay.
right? We want this to come back to minus itself. That was the half. Okay, and when you go through the canonical commutation relations, either by using phase space methods or by doing it in simple ways, you will find what you expect, that psi r, psi s, anti-commutator is equal to del tau r plus s 0. Okay, I'm not going to work that out for you. It's simple. Okay, so what is our Hilbert space then? Also the just a minute.
R means half integer, right?
Half integer, yeah. What? These R and S are whatever appears here. Yeah. Anyway, the delta would, yeah. They have to be minus of each other. Right? Okay, just 1 minute. I'll get you the. Sorry, just 1 minute. Looking at the mode expansion. Right, and okay, fine. Okay, now this expansion here, this psi n expansion, I'm going to take over to the plane. Okay, this half here, okay, the half here, so as you know, this when we go to the plane is going to, okay, so I'm going to write down what this is going to become, and you tell me if this sounds okay. This is going to become psi r into z to the power r plus half, where r belongs to z plus half. Okay, here, whatever we had here was whatever we had here. This is going to become the power of z. So you might think that the expansion should be that whatever we have here should be what power of z we have here. Okay? But there's this extra factor of half, which comes from the conformal dimension of psi, the weight of psi. In going from the cylinder to the plane, there was that extra transformation, the del w by del z to the power h. That gives you this extra factor of half. Okay, this you should think of as the analog of del z, del x is equal to sum over alpha m by z to the power m plus 1. That 1, its ultimate reason, its ultimate explanation was back from del x was a weight 1 operator. Okay, there we worked it out in great detail. I'm not working it out in each case. Here, it's going to be the same thing, right?
But here R is like half integers, right?
Yes, so R belongs to z plus half. Whatever R is, z will come with half more. Okay, so as you say, you can equally write this as sum over R belongs to z, psi R plus half, and then z to the power R plus 1. You could write that equally. Okay? And this is the reason that the NS sector is actually easier than the Ramond sector, this sector where it is periodic. It's because this extra factor of half meets with this half factor here to make it an integer, an analytic expansion, an expansion in poles. Okay? So now that we understand this expansion, we're going to rederive this commutation relation using contour methods. Okay? So from this expansion, we have psi r is equal to, okay, what do I want? I want z to the power r minus half psi of z integral 1 by 2 pi I. Okay? And let's immediately rederive the commutation relations. So the commutation for the commutation relation, we want psi r anti-commutator psi s. Okay? So once again we use our tricks. We have psi r and psi s minus, in this case plus, psi s and psi r. Okay? Once again, the same trick that we used will work. So we want the pole in the psi r, psi s OP integrated over this contour as the answer for the commutation relation. Okay? So let's work it out. So we have psi r is z to the power r plus half psi of z. This is what's being integrated. And then psi s is, let's say, w to the power s plus half psi of w. And here, one of these would have been a psi bar. Right, because it was psi with psi bar, psi with psi star, psi with psi bar. Sorry, this would be psi with psi bar. Okay, so here we want psi bar of w. Now we want the you see immediately that if I did psi with psi, I would get 0. The anti-commutator would be 0 because there's no pole in the OP of psi with psi. Right. So now let's take this OP and look at its pole. Okay, let's take this OP and look at its pole. So we get psi z psi bar w gives us 1 over z minus w, and then there is z to the power r plus half, and then we want we're supposed to Taylor expand this until we get the pole, but we already have a pole, so we just replace this by w. So we have w to the power r plus s plus 1. Okay, so the pole was just w to the power r plus s plus 1. So then we integrate w to the power r plus s plus 1 dw. Okay, and it gives us plus 1 minus 1
Is a minus half.
minus half. Thank you. Minus 1 minus half minus 1 minus 1, and so it tells us, it gives us delta of r plus s. In agreement with this. Is this clear? I'm going through this quickly because we've done this in great detail for the bosons. Anyone who has any questions or confusions, please let me know. Okay? Just wanted to show you that the same contour methods work as well for the fermions as for the bosons. Okay. Let's also quickly understand the state operator map in the NS sector. Okay? Let's quickly understand the state operator map in the NS sector. Okay. First question we're going to ask is, what is the state dual to identity? Okay. By the way, okay. What is the state dual to identity? Okay. So the state dual to identity, so let's see. What we will do is to take this operator psi r and act on the state dual to identity and see what we get. Okay. So that is acting with z to the power r minus half psi of z. So z to the power r minus half psi of z on the state proportional to identity. But that's just doing this path integral z to the power r minus half psi of z 1 by 2 pi I with no insertion out here. Okay, we know psi of z is.
When you define psi bar, was the Hermitian conjugate taken? How was the Hermitian conjugate defined?
Psi bar was just psi star. Okay, just complex conjugate. Complex conjugate. But you know, for every purpose other than purposes of computing inner products, you can just regard psi star as an independent field. Okay? So, think of psi as psi 1 plus I psi 2, and psi bar as psi 1 minus I psi 2, where psi 1 and a psi 2 are completely independent fields.
So, mode expansion would look exactly like that.
Mode expansion will look exactly like this with independent oscillators.
But the e⁻I n plus half would be
Will be exactly the same. Exactly the same. Okay? And that's again because, right. So the mode expansion for psi bar, once again we're going to write psi bar n plus half times e to the power I n plus half sigma plus tau. Yeah. Excellent. And in the when we are interested in actual Hermitian conjugation, so stuff with inner products, it will be psi bar of minus r. So the relation will be psi star of minus s will be equal to the Hermitian conjugate psi bar psi s delta. Okay. Excellent. Excellent. Thank you.
There should there not be a relative minus sign between sigma and tau in psi bar?
No. No. We're just taking Hermitian conjugate, let's say. They obey the same equation of motion. In Lorentzian space.
But psi 1 and psi 2 were like, one was left moving and one was.
Okay, I'm so sorry because we've used psi 1 and psi 2 for two different things. There were psi 1 and psi 2 which were the two elements of the column. Those were left moving and right moving. And then I keep saying in language that you should think of psi. By that I mean psi 1. Now for that psi 2, I've forgotten about it. Okay, after the first 10 minutes of this lecture, the psi 1 and psi 2 where there were two elements of the column, that psi 2 has never appeared again in this lecture. Okay, that anti-holomorphic guy has never appeared again. But what's confusing is I keep saying you can think of psi, which was psi 1, as a linear combination of two real fields, and then I very badly called those psi 1 and psi 2. These are different psi 1. You should call them alpha and beta. So what I was saying was that psi 1 can be thought of as alpha plus I beta by 2, square root 2, and psi 1 bar can be thought of as alpha minus I beta by square root 2.
I'm sorry, what was alpha and beta?
Real fermionic fields. Okay, I've said many times in language in answer to questions that psi and psi bar can be treated as independent fields because they are linear combinations of two independent real fields. And so for almost every algebraic purpose, they can be thought of as independent fields. Just like Z and Z bar in complex analysis can be thought of as independent numbers. The derivative del by del Z at constant Z bar, we do it all the time, right? It doesn't bother us. Same kind of thing.
For that, we are independent in the sense of derivative and integration, but not in the literal sense. That really confuses people.
This confuses people, but every time we have an operation, say we say del by del psi bar, we know exactly what we mean. It is del by del psi 1 plus I del by del psi 2. That's all we mean, right? We call that del by del psi bar because if you define psi bar as psi 1 minus I psi 2 and use the chain rule, that's what we would get. It's a very useful thing, and it's so useful that then you stop thinking of it in terms of psi 1 and psi 2. So in answer to those questions, I kept saying that psi was a linear combination of psi 1 plus I psi 2. By that I meant some two different fields, alpha and I beta. So I'm sorry for the confusion. Are you understanding? Okay. So this alpha and I beta are both holomorphic fields, just like psi and psi bar. The anti-holomorphic field has not made an appearance in this lecture apart from the first 10 minutes. Okay.
Also here, psi, these creation and annihilation operators, psi half with R positive, like R positive half integers.
Yes.
They are like annihilation operators.
Yeah, exactly.
Same as we were.
Exactly. You can read that out from dimensions here. Okay. This whole field has dimension half. Okay. So we can read off the dimensions or energies of these operators. Half. The whole thing has to add up to half, but this guy has dimension, R plus 1.
Yeah, so here the identity here is the vacuum.
Identity is the vacuum. That's what we're trying to derive.
Okay.
Yeah. At the moment but you're exactly on the right track. So at the moment what we've seen is that what we're trying to do is to determine some equations that this identity will obey and thereby identify it as the vacuum. Okay? You may think this is trivial. Okay? And in some sense, maybe it is. In every unitary theory, you can prove that the identity is the vacuum state. Non-unitary theories, this is not true. And as we will see as we go along, I'm not sure how far we'll get today, but as we will see as we go along, in the Ramon sector, the lowest energy state of the Ramon sector will not be the identity operator. Okay? So anyway, we're just checking.
Much as the same as we do in BC CFT.
Exactly. Exactly. BC-CFT, as you know, the identity operator and the vacuum state are different. Yes, exactly. So in this case, you might guess the identity was vacuum and you'd be completely correct, but we're checking it anyway.
But in BC CFT, there is no size 0, right? There is a size 0 kind of thing, right?
Size 0 meaning?
Like like one of the psi 0 will annihilate the upstate and psi bar 0 will annihilate. So they are not two different sectors.
Right. For BC-CFTs, we have a periodicity that is determined from the fact, in string theory, is determined from the fact that C was an infinitesimal diffeomorphism, a ghost for an infinitesimal diffeomorphism. So it has to have the same periodicities as diffeomorphisms. B was a change in a metric, a variation of a metric, so it has to have the same periodicity as metrics. So in that string theory context for BCCFTs, we had no choice about the periodicities. The periodicities came because they were ghosts for particular gauge fixings. Okay? Here we're going to have more choices. This is, yeah, okay, good. Those guys were ghosts. Their role in life was to cancel some bosonic states. That's why they had the periodicities of bosonic modes. Okay? In this case, we're defining a new conformal field theory, a new unitary conformal field theory. Yeah, become clearer as we go on. But let's continue with this. Okay. So we have this here. Now, clearly, if R is greater than or equal to half, if this R here is greater than or equal to half, then this power here is non-negative. Psi is an analytic function. So this integral gives us 0. Okay? And so we conclude that psi R on identity is equal to 0 for all R greater than or equal to half. Clear? Okay? Now, this is in line with what you were saying, because Rajat, right? Yeah. So what you were saying, Rajat, because as you pointed out, the psi R's with positive guys are annihilation operators. Psi R's with negatives are creation operators. Okay, so I did this thing for psi, but you see the same conclusion follows for psi bar, because I just replaced with psi bar here. Okay, so we have psi R bar with identity is equal to 0 for all R greater than or equal to 0. So what we've concluded is that the identity operator is the operator that is annihilated by all annihilation operators. Okay? What was the Hilbert space that followed from this commutation relation? The Hilbert space was that, you see, the Hilbert space was that of a two-state harmonic oscillator, fermionic harmonic oscillator, for every pair of psi and psi bar. Okay? So for every R going from minus infinity, every half integer R going from minus infinity to infinity, we had an independent harmonic oscillator. Okay? And what we've concluded here is that the identity state is the state that is annihilated by all annihilation operators, and so is what we normally associate with the vacuum. Okay? It's the lowest energy state in the problem. We'll talk about energies in a moment when we talk about the stress tensor. Clear?
But usually in fermionic theory, it's a convention. You can say one of the sides as
Well, but not once you know your Hamiltonian. Yeah. So the Hamiltonian tells you which is creation, which is annihilation. Okay. Okay. So very good. Excellent. Now let's try to further understand what we can from the state operator map. Let us look at the state psi of z inserted at the origin. Let's put psi at the, maybe I put psi bar at the origin. Let's redo this calculation. Because psi with psi has no singularity in the OP, once again we conclude that psi r on psi of z, on psi, is equal to 0 for all r greater than or equal to half. That is clear. What about psi bar? We take psi bar of r and act on psi. Now we repeat this calculation. Now this guy here is I'm so sorry, let me put psi because I've done psi. Okay, so psi, this is correct. Now I put psi bar. So I've got psi bar here, and I've got a psi of 0. Is this clear? Okay. Now when I do this, I get a 1 over, this guy becomes 1 over z minus z prime. Z minus 0, 1 over z. And so we conclude that this guy was equal to 0 for all r greater than or equal to 3 by 2. But actually, let's go back to the place where we looked at the insertion of psi. What we got here was correct, but was not the most general thing we could say. Suppose we had psi of z and psi of 0. Okay? Exactly. Not only is this non-singular, because when z goes to 0, this thing vanishes. Because this is an anti-commuting field. Psi of 0 square is 0. This thing is order z. So you see, not only is it true that this vanishes for r greater than or equal to half, it's in fact true for r greater than or equal to minus half. Right? Because with this 1 over z here, we'll cancel the z here. So the first non-analytic term will come from r equals minus 3 by 2. Okay? So actually here, we got that this was equal to minus half. Okay. Now remember that psi bar s and psi r, psi minus s form a conjugate pair for the fermionic oscillator. Okay? Keeping all that in mind and this data, can somebody identify the state? What is the state dual to the operator psi inserted at 0? Psi
Minus 1 over.
minus
Minus half.
minus half on 0. Very good. You take psi minus half on 0. Okay? Because you've got psi minus half of 0, psi bar half does not annihilate it. Because it would annihilate if you took it through. But to take it through, you need to use the anti-commutator and you get a factor of 1. So psi bar half does not annihilate the state. On the other hand, psi minus,
Back to identity.
it brings it back to identity. In fact, we can check that. We'll check that in a minute. On the other hand, psi minus half annihilates the state. Because psi minus half square is 0. Okay? So psi minus half annihilates the state. But psi bar half does not annihilate it. Only 3 by 2 onwards. Okay? Now Rajat was asking, can we see that psi bar half not only does not annihilate the state but brings it back to identity? Okay, let's check that. So we're looking at psi bar half. So this is z to the power 0. Okay, let me write it here. So integral z to the power 0, we have psi bar, okay, and we have psi of 0. Okay, so its pole is just 1 over z. Coefficient of the pole is 1. So that the action of this gives you 1 integrator on the contour, which is just the identity of it. Okay? So this contour trick shows you not only that the zeros are right, but what you get, what's non-zero is also correct. Please. R greater than or equal to minus half? Yeah. Let's do that again. Suppose we were looking at z to the power r minus half, psi of z, psi of 0. We want to know when this is 0. Now, let's look at the OP of psi of z with psi of 0. Okay? First, there's no pole. But in fact, there's something more. Because when z is equal to 0, you get 0 because psi of 0 square is 0. So this quantity, when you Taylor expand it, it starts at order z. There's no constant term because the constant term would have been psi of 0 squared, which is 0. Okay? Therefore, even when you put r equal to minus half, you get something analytic because 1 over z times z. Is this clear? Okay, excellent.
But could it not be that it's even further, ZQ?
It could be. Well, okay. You want to know? Let's actually check. Actually, it's not, because now let's do the Taylor expansion. Okay. The Taylor expansion gives us del psi psi at order z, which is non-zero. Right? You see, OP, after subtracting out the divergent piece, is just Taylor expansion. So in a free field theory, OP is a very simple idea. You get your divergences, which you take into account from 2-point functions, and then the rest within normal order, the ordinary function expansions are correct because there are no singularities. Okay, so it's just that. Okay, let's go. Fine. So, okay, so we understand these this thing. Similarly, by the way, of course, psi. Okay, so we've understood one element in the state operator map. Psi goes to psi minus half. Okay. Now somebody try to make a guess for what psi minus 3 by 2 will be. The state psi minus 3 by 2 acting on 0. What operator will be dualed? What?
Del Z.
Excellent. Del z on psi. Okay, it has the right dimension because it has one energy higher. So in particular, you guys might guess. So let's look at the state. Psi minus of half plus n. Minus of half plus n on 0. I'm claiming that this is the same as del z to the power n on psi. That this state is equal to this. Okay? Let's quickly check that. These are descendant operators of the primary. Yeah, it's correct. It's descendant operators of primary field psi. I haven't yet told you the stress tensor. I haven't yet shown you the size of primary field, but it is. Okay. So let's check this. Okay. So what we want. What we want to do is to see that if this is correct, then many things should happen. First, psi, all positive, all annihilation psis, the creation psi with psi minus, first, this should be annihilated by all annihilation psis. And because, remember, the anti-commutation relation is psi with psi bar. And the creation psi with exactly this number should also annihilate it. Okay, so let's see. Let's do that with psi. So we have z to the power r minus half psi of z, and then del z to the power n of psi of 0. Okay. Great. Now, first, it is completely clear that all r greater than equal to half annihilate this, because psi with psi has no singularity, and so if r is greater than equal to half, this annihilates it. So the annihilation psis clearly annihilate the state. Okay, but now let's look at the creation psis. Okay, so the creation psis are this, right?
Minus half.
What?
Minus half also gives you.
Minus half will give you something, right? Minus half will give you, yeah. So let's work this out. Okay, so what we have here is, if we take so.
Say 2 0 because the psi 0 is just to some number and psi will like what is that, right?
No. But this is not psi. This is del z psi.
But after that you will evaluate at 0, right?
But this is del z. Del z of a field and psi of and the field are different things. Derivative is field here minus field there divided by something. So field here and field here give you 0, but field here and field there don't give you 0. So the derivative is an independent field, independent operator. Okay?
Shouldn't this be psi bar of z?
Shouldn't what be psi bar?
Z to the power r minus half psi bar.
This one? You're saying that this state corresponds to this?
So what you have written here is that we want to see whether psi r bar acting on del n psi, whether it gives back identity or not.
Well, there are two things we want to say. The first thing is, as you say, whether psi bar nth order annihilations
Yeah.
hits and gives identity. That's something we want to check. I was planning to check something else. I was planning to check that this creation operator acting on this state gives 0.
Acting on this state.
This state. Okay, I hope this is clearly written. Half minus of half plus n. So this is a creation operator, but it's a fermionic creation operator. So if I act with the same creation operator again, that squares to 0.
Okay.
Let me first check what you want, Rajat. Oh, I mean, whatever, we can do it in whatever order. So this is one thing we have to check. The other thing we have to check is, look at a psi r minus half, psi bar of z, del z n psi of 0. We can check if you like what you want. Okay, both things we'll check. Let's check what you want. This guy gives us psi bar with psi gives us a 1 by z. You take n derivatives, it becomes 1 by z to the power n plus 1. I'm not keeping numbers. Okay, so we will get z to the power r minus half divided by z to the power n plus 1 integral. Okay, now this guy for r greater than equal to half, okay, for r greater than equal to half, this is 0 except this is 0 except when this thing becomes n. Okay, you need a pole for it to be non-zero. Okay, so all annihilation operators of psi bar annihilated except when r minus half is equal to n. Okay, and therefore except r minus half is equal to n, and therefore except that n is n plus half, which is exactly the Gaia dual to this. Is this clear? So the thing you want is happening, and clearly it will give you identity because it's just 1. Is that clear? Okay. Here, once again, if you expand, you compute this guy. What you would do is expand this in a Taylor series. At nth order, you'll get del z to the power n times del z to the power n. And that will give you the 0. Can I leave that to you to work out? Okay. So fine. I think we understand the state operator map. So the state operator map is sort of clear. And also the multiplication is clear. If you want psi minus half plus S1, psi minus half plus S2 on 0, this will be del S1 psi del S2 psi. That's our operator. Similarly, you can multiply with psi bars. Okay, so you have a sense of the state operator map. It's pretty clear in this situation. Okay. The last thing I want to tell you about before we move on to the Raman sector, and then finally to discuss what I'm really interested in, which is bosonization. Okay. The last thing I wanted to tell you about was about the stress tensor. Okay. So let me give you the formula for the stress tensor. Of course, you get the stress tensor from the usual procedure. Take the action, vary with respect to the metric, and so on. Okay, that usual procedure gives you the stress tensor. I'll just tell you what it is. T. Um, okay, it's just should be just psi bar del psi. I hope I get the minus. Okay, the stress tensor this thing. T is equal to minus psi bar del psi. Again, I may have to change a number or a sign as we proceed. Okay, let's check that this is correct. Okay. First thing I'm going to do is to check the OP of T with psi. Okay. I asserted for you that psi was a primary operator of dimension half. Let's check that that's the case. So we have minus psi bar del psi at z psi of 0.
So we will get this expression by varying the action with respect to the metric. And after that, when we define this T, we have to do a normal ordering.
We have to do always this is normal order. Always, I haven't written it, but always all my expressions like this are normal order. Which means that when you do Wick contractions, you don't contract between this and this. You contract between everything else.
So this recipe, given an action, varied with respect to the metric, you
Yes.
get the action.
The stress tensor.
And then you do the normal ordering. Will this be
Okay.
well-defined object for any arbitrary Q?
Now the normal ordering may or may not be a good. You see, you have to if you have a divergence, you have to regulate it in a way that will preserve all properties of that object. The property that you're really interested in is the fact that it's a conserved quantity. Okay. Now in this theory, normal ordering clearly preserved that because conservation followed from holomorphicity, and the normal ordering preserved that holomorphicity. Okay.
You are adding a
Holomorphic quantity. Yeah. So when you define your operator, in general, what you have to really be careful to do is not change the properties of that operator under the day. Okay. So for instance, dimensional regularization always works, always commutes with equations of motion. Okay. But some cruder regulation schemes don't sometimes. So you may change equations of motion, and in very unfavorable circumstances may even change conservation of the stress tensor if you don't regulate it correctly. So if you do that, then you'll have to add another operator to it to make the thing the conserved stress tensor. So in my experience, dimensional regularization always preserves equations of motion. So if you do dimensional regularization in a complicated interacting case, you're usually on safe grounds. Okay. Okay, but here it's so simple, we don't have to do such fancy things. Yeah. Okay, so now let's look. We want this OP. So there are two contractions. There's this with this, and this with this. Okay, let's first take this with this. So that gives us psi of z del z of 1 by z psi bar of z, and with a minus z. Okay, plus
Psi with psi.
thank you. This is nonsense. Thank you. So first we switch order. We pick up a minus sign. We get del psi of z. Then psi bar of z with psi of 0. Okay. So we get psi bar of z with psi of 0. And so we get 1 over z. No, plus. You see? Look at this. Psi of z, psi bar of z prime is equal to 1 over z minus z prime. Z prime. Therefore, psi bar of z prime, you see, this is negative. Flips under. Okay. Excellent. Wait, so what's going on here? I should have got psi back. I should have got psi back. Why am I not getting it? Just a minute. Oh, no. Because I wrote the stress tensor wrong. Sorry, please forgive me. Of course, it has to be symmetric. It's minus half of psi bar del psi plus psi del bar psi.
Psi bar.
Psi del psi bar. I think it will be this. Give me 1 minute. I just hope there's no minus sign between them. Just 1 second.
Yeah, then only 1 by z square will come. Del on 1 by z will come.
Let me just look it up once, just to be totally sure. He gets del BC minus half del of BC. I think that's minus. Okay, I think he gets. So that's del BC minus del BC by 2 minus B del C by 2. Sorry, minus. The irritating thing in Polchinski's book is that he works at the BC system and then looks at the fermion as a special case of that. It's a slightly irritating thing because then the simpler case you don't have clear formulae for. Okay, yeah. Yeah, okay, this is the stress tensor. Sorry, now let me do it again. Okay. So T is equal to this. So now let's look at, thank you. So now let's look at T of Z psi of 0. Okay. So we get minus half, and just let me check the minus also. SB. I think this should work. Let's hope I haven't messed up my minus. Okay, so we get minus half. Okay. Strange, right? How are we going to get psi and psi bar both? Just one last minute. Del BC minus B del C. Sorry. So it's del BC. Sorry, del BC minus B del C. So without changing the order, the minus came. Yeah. I'm sorry. This was plus. This was plus. This was plus. It clearly had to be. Clearly had to be symmetric between psi and psi bar. Yeah, so clearly, yeah, thank you. Now it should work, thank you. So let's see. So minus half psi del psi plus psi del psi bar del psi plus psi del psi bar on psi of 0. Okay, this is all at z. Okay. So now let's try this one more time. This guy gives us this was a minus, so there's a half. This guy contracting with this gives us plus del psi by z. So plus half del psi by z. Okay, and this guy contracting with this gives us plus psi of z, and then 1 by z. 1 by z square. Okay? And this guy gives us psi bar with psi, which gives us 1 by z. Minus sign when we take the derivative, cancels minus sign of this. But there was a half. Half here. Okay, finally it's working. Okay, now we take the psi of z and Taylor expand it. Okay, so we get del psi, this was at 0 by z into half, plus half del psi of 0 by z from the Taylor expansion. Okay, plus half psi of z by z squared. Okay, so this is equal to h psi of 0 by z, psi of 0 by z square. H psi of 0 by z square plus del psi by z, where h is equal to half, is the holomorphic spin. Yes. Okay. So we see that this has exactly the right form of the OP for the stress tensor with a field with a primary operator of dimension half. All good? We got half because the scaling dimension. H is half. That's why we read off from here that h is half. Okay. Last term manipulation. I'll stop soon. I'm sorry if this class has been a bit jumbled. Sorry, we covered less material than I'd hoped. Okay. Last manipulation, let's try minus half psi bar del psi plus psi del psi bar with minus half this at z and this at 0. Psi bar del psi plus half plus psi del psi bar at 0. Okay. Yes.
Definitely in the expression of T for the psi on shell side, the first term shouldn't vanish. Del psi equal to 0.
Del psi equals 0. Absolutely. It does vanish except when it hits other operators. And the OP is all about hitting other operators. Yeah. Okay. Yeah. Okay. Both these vanish. Because psi and psi bar both are both holomorphic fields. So, right. Excellent. Excellent. So, fine. Let's quickly work this out and then we could go for lunch. I'm sorry for taking so long. Okay, so this is equal to 1 by 4 times psi bar del psi plus psi del psi bar acting on psi bar del psi plus psi del psi bar. Okay, now we've got lots of terms. Let me do the most singular term and I'll leave the rest for you guys to work out. Okay, the most singular term is when you contract everything. Okay, so we have 4 contractions. We have this with this, this with this, this with this, and this with this. Let's do that all carefully. And you guys help me. So when I do this with this guy and this guy is no sign. I have 1 by z, so I get minus 1 by z square. This guy and this guy is no sign. I have 1 by z, so I will get plus 1 by z square because this guy acts on the second guy. So if I'm doing this right, I get the first term is 1 by 4 into 1 by z to the 4. Why minus? 1 minus. First one was minus. Let's see. Just once again, this guy with this guy, z, and then we get a minus. Yes, I agree. Minus. So minus 1. Okay. Then let's do this with itself. Okay. So let's see. So this guy with this guy. Once again, no sign, 1 by z, and then a minus 1 by z square. And this guy with this guy, same thing. So again, I get minus 1 by z to the 4. Okay. Now let's do the cross terms. Okay. So the cross terms have this guy with this guy. So let's do del psi with psi bar. So first we get a minus sign because we take it through with del psi bar. Okay. So let's see. So there's a minus sign. Then we have 1 by z, and then we have 2 derivatives. The first derivative is on one side, so that gives us a minus sign. And the second derivative is on the other side, so it doesn't give us a minus sign, but it gives us a factor of 2. So far I'm getting plus 2 over z cube, where I've taken into account, but did I take into account the minus sign going through? I took that into account. I took that into account because I took a minus sign, and then I took one more minus sign. Yes. Okay. And then there was psi bar with psi, which is just a z cube, z form. Okay. So plus 2 by z to the 4. And I presume the other guy is also plus 2 by z to the 4 for the same reason. Okay. Okay, I think it's identical algebra, right? Okay, and therefore what we are getting is 1 by 4 into 2, into 2 by z to the 4. But, so that is equal to c, yeah, so this is half by z to the 4. But remember that our general Virasoro algebra had c by 2 by z to the 4. So this is telling us that we've got a c equals 1 theory. Okay, and which is correct. Now we've got c equals 1, but note that we were dealing with this complex fermion. We had both, not to confuse with the other psi 1 and psi 2, which will never come again. We had both psi 1 and psi 2, alpha and beta, with two real fermions. If we had been dealing with a single real fermion, that would have been a c equals half theory, just two copies of the same thing. In class, I've worked out the complex fermion because that is what will bosonize. Okay, but this whole theory is the sum of two separate theories. One for the first, a real field psi 1, a real field alpha. Second for real field beta, each of which has c equals half. This complex fermion has c equals 1. The degree of freedom adds. You see, when you have two stress tensors that are just decoupled. Okay, suppose you have T1 which obeys T1 of z, T1 of 0 is equal to C1 by z to the 4 plus 2 T1 of 0 by z squared plus del T1 of 0 by z. And you had a T2 that obeyed as equivalent thing. Now let's say, and T1 with T2 has no singularity because they decouple theories. What does T1 plus T2 do? These parts just add up, right? You get T1 plus T2, T1 plus T2. But here you add. So you get C1 plus C2. So you take two decoupled theories of stress tensor C1 and C2. The net theory is stress tensor C1 plus C2. Okay? So you'll often hear the statement that a free fermion is a conformal field theory with C equals half. And that's correct if you take a real free fermion. We were working with this complex free fermion, which is two real free fermions. That's why we got C equals 1. Okay, since given that it's 120, I will leave you guys to work out the rest of the this OP yourselves. Please do it. It's painful, but it's straightforward. Okay, all you have to do is keep track of the signs. Please do it and check that you get 2t by z squared plus del t by z. This is a good, correct stress tensor. Okay, we should stop. Let me just give you a little appetizer to what we will do next class. So far, we have dealt with one half of the theory. We have dealt with the theory in the NS sector. Okay? Next, we have to deal with the theory in the Ramon sector. The theory in the Ramon sector is complicated, is not complicated, is confusing, because when we do the mode expansion in the Ramon sector, we get a mode expansion in half integer powers. Because of that, none of the operators that we know of, maybe I should say this way, all the operators that we know of, we've taken psi's and their derivatives and their products, and they are in one-to-one map with all the states in the NS sector. That seems to leave nothing for the Ramon sector. What are the operators that are dual to states in the Ramon sector? Okay, we will address that question next class, and in that process I encounter this lovely, old and well-known but still beautiful equivalence between free fermion and free boson theories in 2 dimensions. Okay, please.
Why did you say that partial the sign
Why would on shell psi be this be 0? Because del psi, sorry, you're right, I should have said it wrong. Del bar psi was 0. Sorry, I said it wrong. It was wrong. Sorry.
The reason why you don't create states or particular states for psi bar is because you identify it with
No, you can make states with psi bar. Sorry. So, I gave you all these as examples for psi. But there's also psi bar minus of half plus s.
but do I identify
No, those are just separate. Okay, so the creation operators of psi and creation operators of psi bar create absolutely different states. Okay, and one way to understand that, first you can see it from the algebra. Okay, so how do we see this? First, note that we had a harmonic oscillator for every integer, not every natural number. We get a pair for every integer. And therefore, we have two pairs for every natural number. Okay, that's how you have these two oscillators.
I should think of it as states below for me.
I suppose. Yeah. Okay, but we had a pair of oscillators, creation and annihilation for every integer, not every natural number. Had it been for every natural number, there would have been one oscillator. Okay, okay, great. The other way to think of it is if we're working in terms of psi 1 and psi 2, the independent scalar fields, clearly they have their own oscillators. So there's this doubling.
But I don't use the fact that psi bar minus s is equal to psi dagger.
No, that is not important here. Yeah. Okay. Right. So in the real scalar field, it would have been self-conjugate. So there, psi 1 minus s would have been dagger of psi s, and psi 2 minus s would have been dagger of psi s. Then s would have gone from minus infinity to infinity, but then for each of them, one was creation and one annihilation. Okay, here our numbers went from minus infinity to infinity, and at every point there was one creation and one annihilation. Is what I'm saying clear? Should I write it down? Okay. Yeah. Okay, great. Yeah. So there are really two. It's two sets of harmonic. There are two harmonic oscillators of frequency half. Two harmonic oscillators of frequency 3 halves. That's all. Yeah. Okay. Other questions or comments?
Are those two sectors the periodic condition sector and the anti-periodic
Yeah.
sector?
The Ramond and the Nebel-Schwarz. Yes.
Are those linked?
Linked.
Yeah.
Good.
Because you were saying in the starting that after doing two anti-periodic you get the periodic.
Yes.
So they must be linked, right?
They're linked in the following sense. You cannot include Ramond sector with degeneracy 2 and Nebel-Schwarz sector with degeneracy 1. You have to take a particular linear combination of them. In that sense, they're linked.
I didn't.
Meaning, the full partition function is the sum of the Ramond sector partition function and the Nebel-Schwarz. I have to tell you a little more, but I've not yet told you a little about what happens with left movers and right movers. But anyway, ignoring that for a moment. Okay, the full partition function is the sum of the Nebel-Schwarz, actually NS sector, left movers and right movers. In this class, we totally ignored right movers. We were discriminating, right? We pretended they didn't exist, but they exist. And the full partition function is the sum of the NS sector and the Ramond sector with degeneracy, equal degeneracy. Degeneracy is 1.
But if they are connected, it should not just be sum. We are overcounting, right?
No. It's sum. It's sum just like sum. It was sum for the winding sectors.
Sorry, what do you mean by
I think it's a bit vague in his mind. If you're saying that this is one, that it's a rewriting of the same states, that's not the case. They're different states. It's true there is a connection. You know what the connection will be? The connection will be the following, that in any conformal field theory, the operators that you include in your theory have to be mutually local. You cannot have two operators that have a branch cut as one goes around the other. Okay? And this will be the connection. The connection will be that the set of operators which you retain in your theory, in the Nebel-Schwarz sector, and the set of operators that you retain in the Ramon sector will have to be chosen so that they are mutually local. But that will be the only connection. That's the it will be equivalent to modular elements. You will see. You will see. Once you understand what the operators are, you will see.
The reason this partition function is written in terms of one Ramon,
NS.
Is it because when we do this torus, we have to do plus minus plus minus plus? On the sigma we have to do plus, and on the tau we have to do minus, and there is another way of doing the same sensible identification.
Yeah. This includes one more element that I haven't told you about, which is this GSO projection. So until I tell you about that, I cannot properly explain this point. Okay, you have to also do a projection. Let me say one thing about that and stop. You see, including both these sectors is like including one, if you thought of it in time, is like including a factor of -1 to the f and not including that factor of -1 to the f. So we need to put a projection also in time. I'll explain this next class.